So we didn't get very far into this on Friday. We're going to look over structure of the atom here, a little bit of history of the atom, kind of who's important, but mostly we're going to look at why our idea of the atom has changed over the last few hundred years. Okay, we're going to look at some of the important experiments that were done to kind of prove what the atom looked like, why our model had to change because of those experiments and things like that. Okay, we're also going to look at the basic structure of the atom. What are the three parts of the atom? Anybody remember? Protons, neutrons, and electrons, right? So those are the three kind of main subatomic particles, right? Obviously, nuclear physics has proven that there's even more stuff in there, smaller pieces that electrons and protons and stuff are made up of. There's quarks and things like that. We're not going to get into that. We're just going to look at the main three parts and kind of where they are in the atom, why we think they're there, and things like that. All right, so that hopefully will be review, okay? But the structure of the atom, the models of the atom might be new to you. Okay, so history first. We've been using chemistry for a very long time. We just didn't have a true science for most of that kind of explained why things worked. We just used them because they worked. Okay, we knew that if you put salts in meat, that it would last longer. If you dried it out and salted it and cured it, it would last longer. Stuff wouldn't grow on it. Okay, because salt keeps bacteria and mold from growing. Okay, it was a chemical thing, but it worked. We didn't really know why, but it worked. Okay, we tanned leather, we dyed, clothing and things like that. Okay, using chemicals just because it worked. Okay, you don't necessarily have to understand the science to develop technology that uses it. Okay, and so that's kind of where things started. Was we were able to do things and then had time to figure out why those things worked. Okay, and the reason that science is kind of recent in history is because we now have more time to study questions that we didn't have time to study, let's say 300 years ago, when your main concern was, I got to make sure I have enough food for me and my family every day. Okay, just there wasn't time for that kind of thing. All right, so the earliest idea of the atom was not well accepted. Okay, a Greek thinker named Democritus is the guy that came up with the idea of the atom. Okay, he said, you know what, I'll bet all materials, everything that we use is made up of these tiny particles that you can't see called atoms, okay, or atomos, which is uncuttable. Okay, they would be so small you wouldn't be able to cut them any smaller. All right, the idea didn't go over very well in Greece because other thinkers like Aristotle and Plato and people like that, okay, they thought, no, everything is made up of how many elements? 4. Okay, the Greeks were the people that came up with the idea of earth, air, fire, and water as the 4 basic elements. That idea made way more sense at the time than tiny invisible particles you couldn't see. Okay, yeah, people just were like, yeah, you know what? Maybe you got some bad grapes that day while people were, fanning you in the Acropolis and whatever. Okay, so that idea did not go over well, even though we know now it's actually true. Okay, now why would the Greeks like the idea of the 4 elements better? Because we generally go with an idea that, kind of suits our understanding better. Why would that idea suit their understanding better? Yeah, it was way more intuitive. It made sense. In fact, they had kind of a rudimentary periodic table to do with the 4 elements. Okay, I mean, you live in Greece, volcanoes are part of your reality. Okay, lava was some parts earth and some parts fire and some parts water. Okay, because it could flow like water, it was on fire and very hot, and it obviously came out of the earth. It made sense. Okay, if they were looking at steam, okay, steam was some parts fire, some parts water, and some parts air. Okay, it just made sense. They could kind of reason around what everything was made out of, and it was something that they could explain. Okay, it was something that fit their understanding at the time. Tiny invisible particles just did not fit the understanding of ancient Greeks. Okay, so it wasn't so much that, I mean, yes, it was wrong, but it fit what they knew, right? So unfortunately, his idea was not discussed seriously for 2,000 years. It wasn't all bad for Democritus, though, okay, because being a thinker in Greece was like the best job you could have. Okay, you got to basically sit there and people would fan you with big palm branches and you just had to come up with cool ideas all day. All right, now he did come up with a cool idea. What do you suppose it was, given his name? Democracy, yeah. So it wasn't all bad for Democritus. He just went into politics instead of science, okay, and things then got better for him. So, Okay, now, during the Middle Ages, the science of chemistry was kind of in its early stages. It wasn't a true science yet, because a true science involves, having using the scientific method, having a hypothesis that's tested under controlled conditions, communicating your results. Okay, and that's probably the most important part of science, is communicating your results with other people for peer review or peer repetition. Okay, you have an experiment that works, you're able to repeat it a couple of times. You need to make sure somebody else can do that same experiment and get the same results in order for it to be valid. Okay. In the early stages of chemistry, that wasn't what happened. Okay, we had these people called the alchemists. Okay, and the alchemists had discovered that when you put things together, sometimes you got surprising, maybe even valuable results. Okay, so what they were trying to do is they were trying to do things that we now know are impossible. They were trying to turn common substances into gold. Okay, they were trying to develop the elixir of life, this drink that you could drink and you would live forever. Okay, unfortunately, a lot of those did not work out very well, and a lot of people died testing those. Okay, and a lot of experiments would have gone awry. Okay, because they didn't use any scientific method of any kind. They just hid in their little labs that would have looked something like Da Vinci's lab here. Okay, and they just mixed stuff together. Okay, they would have been your kind of stereotypical, kind of wizard-looking kind of person who would have just, had a mortar and pestle and mixed things together and occasionally blew stuff up. All right. And so it was all trial and error. Okay, they didn't record results. They certainly didn't share results, because they didn't want anyone to use something they discovered and get rich off of it before they could. Okay, it was very secretive, and as a result, even though now we look back on it and we say, okay, well, they discovered some valuable things, that wasn't discovered until much later, because they wouldn't communicate those results. So while they did some rudimentary discovering, okay, they didn't contribute a whole heck of a lot to the science of chemistry. Okay. Now, the science of chemistry took off basically when most of the sciences took off, and that's when Antoine Lavoisier and Roger Bacon, okay, developed the scientific method. Okay? The scientific method involved having a way to test an idea in a controlled manner. And what I mean by that is, they would have a problem that they were investigating. They would make a prediction about what the cause of that problem would be, so a hypothesis. Okay, they would have a manipulated variable, a responding variable, and then a bunch of controlled variables to make sure the experiment ran the way they wanted it to. Okay, and then they would test it. They would analyze the results. They would come up with a conclusion, and then they would communicate those results to other people. So the scientific method is what turned alchemy into chemistry. Okay, yeah, they still did a lot of the same things. They tested stuff out, but now they were using it under much more controlled conditions, and they were communicating it with others for other people to analyze their results and see if they came up with the same ideas. Okay, so those guys are pretty important for all sciences, because they're the guys who developed the scientific method. Okay, all right. Okay, so the idea of the atom. Okay, if I have a hunk of lead, let's say, in my hand, okay, does it have atoms in it? Okay, are all of those atoms the same? Yes. Okay, all of the atoms in just a hunk of lead are identical, because they're all lead atoms. Now, I say identical, there's going to be small differences in some of them called isotopes, but for all intents and purposes, they're all the same. Okay, if I kept cutting that chunk of lead into smaller and smaller pieces, okay, eventually I would get down to the point where I would have single atoms. Now, obviously, I don't have anything that can cut that small, but theoretically, if I could do that, okay, I would eventually have a table covered with all these individual atoms, okay, that are all identical. That would be the basic unit of that particular element, okay, and they would all be the same. Okay? Now, the reason they would all be the same is because their atomic structure would be identical. That is, they would have the same number of protons and the same number of electrons. Okay? And for most of them, also the same number of neutrons. Okay? It's the number of protons in an atom that determines its properties, that makes it what it is. All right, so if we're looking at the periodic table, I gave those out on Friday, right? Gave everybody out their periodic table? Okay, so if I'm looking at the periodic table here, okay, and I'm looking at lead, because that's what we said we had, okay, every lead atom has 82 protons in its nucleus. Okay, because it has 82 protons in its nucleus, it has the properties of lead. Okay, if I had a different atom, okay, that only had 19 protons in its nucleus, then I'd be looking at potassium. It has much different properties than lead does. okay, because it's different, it has a different atomic structure, right? So it's the number of protons in a nucleus that determines the properties of the atom, okay? Now, originally, the original idea of the atom said that the atom is uncuttable, okay? You can't split it, you can't make it smaller. Is that still true? No, okay? It's true in a natural sense, okay? There's no kind of natural thing that's going to cause a fission reaction to happen. Some things are radioactive, they spontaneously break down, but they don't explode, okay? We do know that through artificial means and through the proper technology, yes, we can split certain atoms, not all atoms, certain atoms, okay? What kind, big or small? Big. The bigger an atom is, the easier it is to break, okay? Because A, it's a bigger target, and B, the bigger they get, the less the forces that hold the atom together work. Okay, because the spaces between the particles that are supposed to be attracting each other together, okay, the bigger those spaces get, the weaker the forces holding them together will get, okay, and so the bigger an atom gets, generally the less stable they become, and that's why on your periodic table at the bottom, you see all these elements here that have been kind of recently discovered, okay, these are all man-made, okay, they're made in like in the big colliders and things like that, and they don't last very long, they spontaneously break down, they last for sometimes tenths of a second or less, okay, they only know that they're there by using kind of a mass spectrometer to identify them, but they break down very quickly because large atoms are typically not very stable, right? So the ones that we do know of that are stable, okay, are obviously all on there, and they are not going to have the hollowed out lettering, okay, like these ones do. Okay, so right, so the atom then is the smallest particle of an element that retains the properties of that element. So there's basically two kinds of ways to modify the nucleus of an atom. Okay, there's fission, which is splitting the atom, and then there's fusion, which is forcing the nuclei of two or more atoms together. Okay, both of them result in a large energy release. Okay, so if we're looking at a fission reaction, there's two ways to have a fission reaction: a controlled one and an uncontrolled one. One is how you make electricity, the other is how you make destruction. All right, so if we're looking at let's say, making electricity in a nuclear power plant, in the nuclear power plant, they'll have what are called fuel rods. Okay, on the fuel rods will be enriched pellets of uranium. Okay, these rods are lowered into the path of particles, high-speed particles. Okay, when those high-speed particles hit the fuel pellets, they cause them to split. Okay, because they're made of these big uranium atoms. Okay, what that does is this reaction always occurs in water. Okay, so the water heats up, turns to steam, steam turns a turbine, which generates electricity. Okay, so that's kind of the process of making electricity using the atom. Okay, making destruction using an atom, okay, involves one small explosion and one big explosion. Okay, so in the simplest sense, I'm telling you how to build a nuclear bomb. Because, well, you won't be able to build one. But anyway, it's generally how it works. Okay, you would have a shaped charge. Okay, so you'd have like plastic explosive, C4 or something like that. Okay, and you would have it shaped so that when you detonate it, the explosion is focused inward onto some enriched plutonium, okay, some kind of fissionable nuclear material. All right, when this stuff here explodes, the particles from the explosion are directed inwards at this thing, and when they strike it, they cause an uncontrolled chain reaction, okay, that results in the detonation of a nuclear weapon. Right? That's in a very simple sense. Obviously, there's way more to it than that, okay, but it's essentially that's how it works. Okay, but we get that stuff to essentially split, and then we get a whole bunch of different kinds of atoms formed after that, and a lot of energy obviously released, and a lot of radioactive material spewed everywhere. All right, so that way is bad. Okay, this way is controlled. Okay, if I need to make more electricity, I just expose more of the fuel rod to the path of the particles. Okay, if I'm getting too much or it's getting too hot, then I pull the rod back out, okay, or expose less of it to that. And that's what happened at Chernobyl. The thing that was supposed to pull the rods out malfunctioned, and so the fission reaction continued until all the water had evaporated, and then what happens is it gets really, really hot and literally melts down. Okay, that's why it's called a meltdown. Okay, it literally melts everything around it. Okay, in fact, they've got it in the old Chernobyl reactor. There's this thing called the elephant's foot, and it's the big lump of radioactive material that melted out of the reactor core, and it's just sitting there. Okay, like it's just, and it's going to be radioactively hot for hundreds of years. Okay, and it's just there, melted down everything around it. Okay, does that sort of make sense? Okay, so the nucleus of the atom is the part that determines the properties of the atom itself. Okay, okay, so late 1700s, okay, chemistry is going along nicely. Okay, people are discovering how reactions work and when they mix things together, okay, why certain reactions occur, how you can make stuff, okay. But what they've discovered is that what the alchemists were trying to do can't be done, or at least they haven't figured out a way to do it. And that is, how can I change something cheap like lead into something valuable like gold? All right. What they've discovered is there's really seems to be no way to do that. Okay. Why is there no way to do that? Right. Their atoms are different. Okay. They're different elements. I can't turn an atom that has 82 protons in it into an atom that has a different number of protons in it. Okay, like gold is got 79. I can't just go, oh well, I'm going to pluck 3 protons out of every nucleus, a few neutrons, take a couple of electrons out of there, and boom, suddenly I've got something else. Okay, we can't do that. We can't alter an atom to turn it into another kind of atom. Okay, now in a nuclear explosion, yes, that happens, but it's not something controlled. We can't go, well, if I split the atom this way, I'll get this. It doesn't work. Okay, and so that was one of the things that chemistry had discovered, okay, along the way. So Dalton had been looking and reading over other people's research, and he came up with the idea, or the atomic theory. Okay, the ideas that essentially govern what we know about the behavior of matter. So these 4 points are super important. So if you are highlighting or in some way marking these in your notes package, these 4 points are super important. Okay, so John Dalton is the guy that came up with this. Okay, it's Dalton's atomic theory. Okay, first point of the atomic theory came from Democritus. Okay, he realized that when reactions occur, the only way to explain what happened was for tiny particles to be changing places, bonding with each other, moving around. Okay, and so he went back to the idea that Democritus had, that all elements are composed of these tiny, indivisible, not invisible, indivisible, okay, so you can't split them, okay, particles called atoms. Okay. He also said that atoms of the same element are identical. There's no way to have a bunch of carbon and have all the little particles be different. If they all have the same properties, they all have to be the same. So that was kind of where that idea came from. Okay, the atoms of any one element are different from those of any other element. Right? And again, Dalton is saying all this stuff before we know about protons, before we know about neutrons, before we know about electrons. Okay, he has no idea what an atom looks like when he's developing this theory. This is all based on watching chemistry take place, looking at the behavior of matter during chemical reactions, during physical and chemical changes and things like that. He's inferring essentially all of this without any real like particle evidence for it. Okay. Third point, and the third point is pretty important, okay, because it talks about what happens in a chemical reaction. Okay, atoms of different elements can combine with one another in simple whole number ratios to form compounds. All right, so he said, not everything is made of a single atom. Some things are made of more than one atom and more than one kind of atom, and those things are called compounds. Okay. The other thing he said here that's really important is about simple whole number ratios. Okay. Basically, he said atoms don't split when they form compounds. Okay. So if we're looking at a very common compound, like water, okay, it has how many hydrogens? 2. And how many oxygens? 1. Okay, now I could write it like this and I'd have the same ratio. I could write, but can I have half an oxygen atom? No. Okay, half an oxygen atom, okay, if I go over here, oxygen is, it's got 8 protons in it. Half an oxygen atom would be beryllium. Not the same thing. Okay, that's what he means by simple whole number ratios. And when you have a compound, it is going to have whole atoms only. Okay, they don't break apart in order to make a new compound, right? So they're only ever written like this. That's why all the chemical compounds you've probably encountered, okay, never had any fractions in them. They're always going to be simple whole number ratios. Okay, and the last point, and this point here is the one that killed alchemy forever. Okay, chemical reactions occur when atoms are separated. Okay, so if I had water, I would separate the hydrogen from the oxygen. I don't mean pulling an atom apart. I mean pulling different atoms away from each other. Okay, so they can be separated, or they can be joined, put together. Okay, or they can be rearranged. Right, so what that looks like, okay, in a chemical reaction, I'll show you here in a second, okay, but this is the part that killed alchemy. However, atoms of one element are not changed into atoms of another by a chemical reaction. Okay, this was what the alchemists got wrong. When they saw a chemical reaction happen, like let's say this one, okay, so this reaction here involves mixing lead nitrate with potassium iodide. When that happens, okay, the reactants are two clear solutions. Okay, so if an alchemist did this, he would start out with two things that look like water. Okay, two clear solutions. When you mix them together, a reaction occurs. A bright yellow precipitate or powder forms in this reaction and settles to the bottom with a kind of clearish solution above it. Okay, it looks very different than what you started with. Agreed? Okay, so what alchemists thought when they did this is they said, I magically changed this stuff into something else. Okay, they didn't realize that they were just rearranging the atoms and whose partners they were with. Okay, they thought they were physically changing what they had. Okay, they didn't realize that they still have the same atoms on both sides of the reaction. Okay, but they thought they didn't. They thought they had magically changed it into some other material. Okay, so in a chemical reaction like this one, okay, this is the rearrangement part. Okay, on this side of the reaction, which we call the reactants, okay, lead is with nitrate, potassium is with iodide. Okay, on this side, lead's with iodine, and potassium is with nitrate. Okay, they've switched partners, but it's still all the same atoms I had before. I still have nitrogen atoms, oxygen atoms, potassium atoms, lead atoms, and iodine atoms. Okay, I haven't created anything new. Okay, I also haven't suddenly destroyed anything. Okay, everybody all right with that idea? Okay, so that would be a rearrangement reaction. Okay, this could be a joining reaction. Okay, if I reacted magnesium metal with chlorine gas, I would get this, magnesium chloride. Okay, I've joined those two atoms. I haven't changed anything. I still have magnesium and chlorine on both sides of the reaction. Okay, something could be separated. Okay, this is the process by which rocket fuel is made. Okay, we separate hydrogen and oxygen from each other, and we create liquid hydrogen, liquid oxygen, and that's what makes rocket fuel. Okay, but I still have on both sides of that reaction hydrogen and oxygen. Okay, so this is what Dalton had realized by reading other people's research, by doing his own experiments. He realized that when he did when he caused a reaction to happen, he still had the same stuff he started with. It just had been somehow rearranged. Okay, everyone all right with that idea? Okay, so the 4 points of the atomic theory are definitely something you need to know and understand. Okay, so that explanation there about what happens in a reaction goes along with 3 and 4. Okay. All right, Dalton comes up with this idea. It makes good sense. People accept it, but they have a follow-up question. What do you suppose it is? not so much how do we know this, because he had a lot of evidence to go along. He could say, in this reaction, look what happened, but it's still the same stuff that I started with. The big thing was to do with point number 1. What do atoms look like? You can't see them. And everyone's like, well, that's a cop-out. Like, that's not good enough. We can't see them. They're too small. That's convenient. Okay. No, he had to come up with something, okay, that could explain this. And again, this is before we know about protons, neutrons, electrons. So he took the most common shape in nature that he could think of, a sphere. Okay. The Earth is a sphere. If you're a flat Earth person, you're not going to like anything I say in this course because that's craziness. Okay. But the Earth is round, all the planets are round, the moon is round. Okay. Spheres were, okay, a very common shape. It made sense to say, well, you know what? Maybe that basic piece of matter is shaped like a sphere. People are like, okay, can't see it anyway, so we'll go with that. Okay. So for the first little while, this is what everybody thought the atom looked like. Okay. We called it Dalton's solid sphere model. Okay. So the first model of the atom was the solid sphere. Okay. And because we didn't understand exactly what happened in a chemical reaction in terms of the movement of electrons and things like that, this idea stayed for a very long time. Okay. People accepted it, okay, because there really wasn't anything to say that it was wrong. And that's usually the way science goes. We keep an idea until somebody does an experiment that doesn't fit with that idea anymore. Okay? Then we either have to say something was wrong with the experiment or something was wrong with the idea. All right? And sometimes we're a little slow to say something was wrong with the idea. Okay? Prime example would be classifying all living things into 2 kingdoms. Okay? When your parents went to high school, okay, even when I went to high school, okay, there was still a group of people who said everything is either plant or animal. All right, there were only 2 kingdoms for all living things, plants and animals, and we just jammed stuff into those things because we didn't want to change our idea, even though we knew that, like a fungus, that got put in the plant kingdom. Okay, mushrooms were a plant according to that idea. Okay, what's wrong with that? Yeah, they don't care about photosynthesis, which is a defining characteristic of plants. Okay, we also put all the bacteria and things like that in the plant kingdom because, well, they weren't animals. So they must be a plant. Okay, didn't care about photosynthesis either, but man, heaven forbid we should change our thinking a little bit and see if we could think up a better system. Okay, now there's like the 5 kingdom system, even like 7 kingdom system, depending on which way you go. Okay, that includes a kingdom for all bacteria, a kingdom for fungus, a kingdom for the protists, the single-celled eukaryotic organisms that don't really fit anywhere else, and so on and so on. Okay, we have to change our thinking when we start coming up and discovering new things. All right. Okay. So, late 1700s is when Dalton comes up with the solid sphere idea. It's almost 100 years before somebody performs an experiment that says something might be wrong with this idea. Okay? And that person is J.J. Thompson. Okay? J.J. Thompson was performing experiments with electrochemistry, right? Working with trying to make like a cell, a battery, okay, kind of a thing. And so he found that some chemical reactions could produce an electric current. It was pretty hard to explain using Dalton's solid sphere model how moving charges could happen if atoms were a solid sphere. Okay? If atoms were a solid sphere, the only explanation for an electrical current to occur through a chemical reaction was for atoms, solid spheres, to travel through the wire. And the wire is solid, and it was made of copper. So there was no way that atoms that were in this reaction could be moving through it. Okay, so there had to be something wrong with the solid sphere model because it couldn't explain where these charges came from and what they were. Right? So what Thompson said is there's really nothing inherently wrong with an atom looking like a sphere, but there has to be 2 parts to it. One part that's negatively charged that can fall off and travel through the wire, thus it's even smaller than the rest of the atom, and then the rest of the atom can be positively charged. Right? So he came up with what he called the plum pudding model. Okay? He said an atom is a solid sphere, but there's like these plums stuck to it that are electrons, okay, that can fall off during a chemical reaction. Maybe the atoms run into each other and these electrons get jarred loose and they come off and they create the electric current that flows from one side of this thing to another, okay, something along those lines, okay. But he had to change the model of the atom because the other didn't explain where those charges came from, okay. So then we had Thompson, okay, so J.J. Thompson with his plum pudding model. Right, so we've had the first experiment that didn't fit with the idea. Now, at the turn of the 20th century, okay, there was a lot of research going into like physics and structure of the atom and stuff like that. People were devising like really crazy experiments. We were starting to discover radioactivity. Okay, radioactivity was one of the reasons why J.J. Thompson's model didn't last very long, because his model could not explain high-speed particles being essentially produced from certain atoms, okay, like uranium and things like that. Okay, so we were discovering those things, and that couldn't really explain this, because then the pieces that would come off during radioactivity would have to be very, very large, and they're not. Okay, so this model didn't last very long. A lot of different models were proposed during like the next 40 years or so, okay? Some of them involve still like a solid sphere, but with lots of different particles stuck to it, okay? Or electrons orbiting a positive nucleus or a positive particle. Maybe they weren't actually stuck to it. Maybe they actually circled it like planets, okay? Lots of different ideas were proposed, okay? Because we were starting to discover that there's other parts, okay? Like the proton, for example, okay? Protons were discovered, okay? That kind of said, well, the plum pudding model and the solid sphere model don't explain this, so we have to come up with something else. Okay, neutrons were discovered shortly thereafter, also not explained by the plum pudding model. Okay, so that model had to be rejected. Okay, and at this point, there's essentially like chaos within the physics and chemistry community because nobody has any idea anymore what the atom looks like. Nobody can agree. There's lots of different ideas. None of them can be proven. Okay, so there's a lot of argument and things like that. Okay, so James Chadwick discovered that protons were not the only large particle in the atom. He found that the mass of many elements was too large to be accounted for by only protons. So what we're saying here is when he would have a sample of something, he had a pretty good idea of how many particles should be in that sample. But according to that idea, there had to be something else in the atom to account for all the mass. Otherwise, protons were huge, and they had a pretty good idea that protons weren't huge. Okay? So they had to come up with this other particle that would also be in the nucleus, but it couldn't have a charge. It just had to account for mass. Okay, that's where the idea of neutrons came from. Neutrons are exactly the same mass as a proton, but carry no charge. Okay, so they help to make up the rest of that mass. All right. So Ernest Rutherford is the next really, really important guy. Okay, like Dalton and Rutherford are the two most important people when it comes to structure of the atom. Okay, because Dalton's the guy who said atoms exist. Rutherford's the guy who proved what they look like, essentially. Okay, so Rutherford was in favor of the nuclear model of the atom. That is, that there was a central dense nucleus that contained positively charged particles and neutrally charged particles, and there were electrons that went around that orbited it. He, however, believed the nucleus was very, very large. Okay, he believed the nucleus was really, really small. Okay, like tiny. And so he was going to devise an experiment that could prove that the nucleus A existed and B was really small. Okay, pretty hard thing to do for something you can't even see. So what he did is he took a setup like this. Okay, he had a very thin piece of gold foil. So imagine like tin foil, like you would use on a baked potato. Okay, but he had that. It was made out of gold, and it was really, really thin. Okay, and he placed it in the path of some alpha particles. So essentially like an X-ray machine. Okay, and he said, what I'm going to do is I'm going to shoot these alpha particles at the foil, and I'm going to surround the foil with photographic film. Okay, now here's a generation gap. Cameras used to come with this stuff in them called film. Okay, and when you would push the button, the shutter would open and light would go in and expose the film, and that's how you made a picture. Okay, so anytime photographic film is exposed to light, it changes color, essentially, okay? So the same is true for photographic film and X-rays, because that's how you get an X-ray, okay? So he said, if I run this experiment and the nuclei of these atoms are really, really small, then all of the particles will go right through and I'll only get a bright spot on the photographic film behind, okay? Because the particles I'm shooting will be, they'll just go through. The atoms are so small that there'll be a lot of space in between them, right? Well, what happened was when he ran this experiment, he got bright spots in a lot of different places. Yes, the bulk of them ended up back here, but they weren't all in one spot. They were deflected slightly. And the only way that could be explained was if those particles, some of them went straight through because the nucleus is small, okay? But some of them would hit the nucleus of an atom, and that would deflect them off on a different path. So they would end up, let's say, over here instead of straight behind, right? This was shocking to Rutherford. He said it was like shooting a shell, like an artillery shell at a sheet of paper and having it bounce back. He said it was amazing that some of these particles were actually hitting stuff because he thought the nucleus of the atom was even smaller, okay? So what his experiment proved was, first off, there's a nucleus. If there wasn't a nucleus, then either all the particles would have gone through or none of them would have got through. If this was a solid sphere model, basically none of them would have got through, okay? But there's lots of space between the atoms, okay? There's a nucleus and then there's a lot of empty space around it, right? So he proved with this experiment the nuclear model of the atom, and that's why he's so important, okay? The gold foil experiment, okay? So we'll just say Rutherford, okay? And the gold foil experiment, okay, proved the nucleus. Okay, that's what we need to know in shorthand about Ernest Rutherford. Okay, his gold foil experiment proved the existence of the nucleus. Now, you'd think at this point everybody would be kind of happy, right? Because, oh, great, now we know, where protons are, we know where neutrons are, we know where electrons are, we got a good idea of what the nucleus looks like. Now we can build nuclear bombs and things like that, because that we couldn't build nuclear bombs until we knew about the nucleus. So this was an important development. Okay, so you'd think everybody would be fairly happy with this idea, except they weren't, because scientists are never happy. They always want to discover something else. So the next argument was, all right, fine. The protons and the neutrons are in the nucleus. What are the electrons doing? We know they're around the nucleus. We know they're not in it. What are they doing? Are they in like orbits like planets around the sun? Do they offset each other? They're all the same distance away. How do they not run into each other? How do they not crash into the nucleus? How does, how is it that when I put something fluorescent under an ultraviolet light or in the sunlight, okay, and then I move it away, that it still glows in the dark afterwards? How are these things all explained? Okay, that, it's great that the nucleus is around, but how do we explain this other stuff? Okay. So the rest of the stuff to do with the model of the atom had to do with what the electrons are doing. Okay, all our subsequent models of the atom still include the nucleus because we know that's true. Okay, the rest of the argument was, what are the electrons doing? Okay, now the idea of the electron, okay, has to do with, the idea of where the electrons are has a lot to do with energy. The more energized an atom is, the further away from the nucleus, generally, electrons can be found, because they'll pick up energy and they'll pick up speed and they'll jump. They'll make what's called a quantum leap from one energy level to another. Okay? If the energy source that's making them move is removed, they'll begin to lose energy and they'll fall back down to lower energy levels. When they do that, they give off the energy that they had gained. Right? That's how glow-in-the-dark materials will glow in the dark for a short period of time after they've been in the light. Okay? It's also how plants carry out photosynthesis. Okay? The chlorophyll molecule has obviously atoms which have electrons. When the chlorophyll molecule gets excited, that is, gets hit by light, the electrons will move to higher energy levels. When the light goes away, those energized electrons fall back down. The energy they release is used to break apart carbon dioxide and water and form sugar and oxygen. Okay, that's the source of energy for photosynthesis. People knew that that's kind of what was going on, and so that was why they had so much argument, or why they did so much arguing over where are the electrons? What do they look like? Okay, so what we've generally come up with is two models that are reasonably acceptable. Okay, if I took a picture of an atom and froze it in time, the electrons would look something like this, like the Bohr model of the atom. Okay, they would look like planets orbiting the sun, except some of them would share the same ring. Okay, and they would move around like this. Okay, but if I take a snapshot of it, this is what I would see. Okay, obviously though, an atom is always changing, so a snapshot isn't exactly what we're looking for. Okay, what's more likely to be true is this, the de Broglie electron cloud model. Okay, that is that yes, there are what we call orbitals, areas where an electron is likely to be found, but those orbitals are, whether an electron is in that orbital or not, is based on the structure of the atom and the energy of the electrons. Right? So certain orbitals are going to be more populated than others. So you can see here that every little dot here is an electron. Okay, so these are the areas where electrons would be likely to be found. Okay, the ones that are further away, the higher energy levels, are less likely to be populated by an electron, so they're less dense out there. Okay, but essentially what it means is there's an area where I could find an electron. It could be there or not. It's a Schrodinger's cat thing. Okay, sometimes there's an electron there, sometimes there's not. It all depends on the energy of it. Okay, but there's all kinds of different shapes to these orbitals, okay, and different energy levels for each of them. All right, so this is what we generally accept, okay, the electron cloud model, okay, which includes a nucleus with protons and neutrons, and then electrons found in various places called orbitals, okay, around the nucleus. So the de Broglie model, okay, is the currently accepted model, de Broglie's electron cloud. Okay, I'm going to give you about a 5-minute break here because I've been talking steady since we started. Okay, so I'm going to give you about a 5-minute break. You want to check your snaps or whatever, okay? Give you 5 minutes to do that. Okay, so we got de Broglie's electron cloud model, which essentially means, okay, we've got the dense nucleus here in the middle, okay, and then we've got areas where electrons are likely to be found based on their energies, okay, so that can be some that are close, okay, those would be low energy orbitals, those are probably occupied most of the time, okay, and then we would have higher energy ones, okay, that are further away that are going to be less often occupied. Okay, unless there's some sort of weird energy thing going on, okay, with the electrons, right? So essentially, de Broglie said, yes, it's a cloud, but there are regions within that cloud that are more likely to contain the electrons. Those are called orbitals, not orbits because they're not circular, okay? Orbitals, that's an area where it's likely to be found. So we'd have the nucleus here in the middle, okay? And then this first one here would be the 1s orbital. That's the lowest energy one, okay? Most likely to have stuff in it, okay? Then we would have the different 2-level ones, okay? So we'd have 2s, 2p, okay? And so on. They're getting weird shapes. Why are they getting these kind of lobes and things like that, you suppose? Like, why wouldn't they just have perfect circles? What charge do all electrons have? It's negative. Right? They repel each other. If they get too close, they're going to repel. Okay? So there are regions where they're going to be found based on the fact that if they get too close to another one, they're going to push away from each other. Okay? They're also obviously attracted to the nucleus because the nucleus is positively charged. Okay? So there's a lot of interactions there between repulsion and attraction, okay, that kind of determine where they're going to be. Okay? And then obviously we got higher energy ones out here. This doesn't include all of them, just includes some of the more common ones, okay, the lower energy ones. Okay, so all atoms are made of protons, neutrons, and electrons. They're all made of the same basic parts. Okay, what makes all atoms different, we already talked about, okay, but here's the answer. Okay, the reason that all atoms are different is, okay, the number of protons in their nucleus, not the number of electrons, not the number of neutrons. It's the number of protons that determines the physical properties of an atom. Okay, and that's what the atomic number of each element tells us. Okay, so if we're looking here, like hydrogen's got how many protons? 1. Okay, and helium would have 2, and so on, and so on. Now, one of the things you're going to be expected to be able to do is draw me a picture of an atom. All right, so which model should you draw? Which one do we currently accept? The electron cloud model. Okay, now within that model, you're going to have to show me the correct number of protons, neutrons, and electrons. All right, so let's pick kind of a one that's not got too many particles in it. Let's say we're going to draw a picture of let's say a fluorine atom. Okay, let's go with fluorine. All right, so in a fluorine atom, in the nucleus, there are going to be how many protons? 9. Okay, so I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, and I'll probably put like a plus sign inside of all of those. Okay, so that I know there are 9 protons. How many neutrons are there? That's a little tougher, right? 10. Here's how you figure out how many neutrons there are. Okay, you take the atomic mass, and for you guys, the atomic mass of fluorine is 19.00 grams per mole. Okay, and you subtract the atomic number. So, okay, we subtract 9. That takes care of all the protons. That leaves me with 10 neutrons. Now, it doesn't always come out to a perfect number. Okay, with fluorine, it sort of does. Okay, but with other atoms, it might not. What if it came out to like, let's say, 18.1? Well, it'd just be like if I did this operation, instead of coming out to 10.00, it came out to 18.1. Can I have 0.1 neutrons? No, just round it. Yeah. Okay. I'd say there's 18. All right. There's 18 neutrons. Most of the time, it's pretty obvious because it's going to be really close to one or the other. It almost never ends up halfway in the middle. All right. So there's 10 neutrons. So I just got to put another 10 particles in here. All right. So there's my nucleus. All right. How many electrons are there? 9. Number of electrons is always equal to the number of protons in an atom. Okay, if the atom has turned into an ion, then that's not true. But okay, if I'm asking you to draw an atom, then it would be true. So what I would do, okay, is I would just say like, and then I might do this to indicate that those electrons are somewhere in the cloud. Okay, and then I've said, all right, I drew de Broglie's electron cloud model. Okay, so I know which model we accept. I got the right number of electrons, I got the right number of protons, I got the right number of neutrons. Okay, I'm going to get full marks on this question. All right, there has not been a unit exam in the past 7 years where I did not ask you to do exactly that. Hint, hint. Okay. All right, questions on that? Okay. Right. Maybe we should, I'll label this here. If you didn't write this down, okay. Okay, so to calculate the number of neutrons, you take the atomic mass and you subtract the atomic number. Okay, has to be a whole number. You can't have 0.2 neutrons. Okay, anybody need that one anymore? All right, so in your workbook, the digital workbook, you will find these 12 questions here on atomic theory. All right, what I would like you to do is to answer those questions using complete sentences. Okay, the answers are either directly out of the notes or you have to use your head a little bit with what's in the notes in order to answer them. Okay, but this is exactly the kind of thing that could end up on tomorrow's quiz, because tomorrow is Tuesday and you have quizzes on Tuesdays and Thursdays. So this is the kind of thing that could end up on that. So I'm going to give you guys some time here to work on that. I would imagine we might even be able to go through the answers to these before the bell goes today. All right, so let's make good answers for these, okay, and we'll get going on that.